Go.
Okay. Hello everyone, my name is Thomas J. Bottolato. Most of you know me as TJ, and I'm here today to present you my project on my balancing robot. Before I begin, I'd like to just give out some acknowledgments. I'd like to thank both my parents for being here today and their continued love and support throughout my life. I'd like to thank my girlfriend for being my Van White today and advancing slides for me, as well as her patience throughout this entire process. I want to thank Dr. Jula for being my technical advisor and all the drive that he gave me to continue forward with this project. Professor Ebel for all her being on point for this class. You know, there was really never any question as far as what was due of me and when it was due and stuff like that. And her positive words of encouragement really helped me out through the process. So with that, I will continue forward and show you what I've done for the past year. So the topics that will be covered, I'll be going over a brief project description, followed by my requirements and specifications that were developed in the beginning of this process. I will then follow through with the functional decomposition and the choice of the subsystems. And then the end of it will be my testing, the results that I got from that testing, followed by the cost, the schedule that I followed, the conclusions that I have, and I'll open the floor to any questions that anybody might have. So here we have an image of what was constructed. You can see on the left-hand side that is an image that was made in the spring semester using SolidWorks software. And you can see on the right-hand side that the final product looks very, very much like what was thought of in the beginning. In the end, the only difference that you can see is on the base of the robot. I have the two batteries. They were added at the end of the process, but other than that, everything followed exactly as I thought. So brief project description. This is a classic control system trying to stabilize an unstable system. The reason I chose this project is because it's a great mixture of many modern technologies. The use of an IMU and the filtering required to use that is very broad. It's used, you can see on the bottom here, it's used in aircraft, space travel, and most of you know what the Segway is, and this is a very good example of that. The market that this could be marketed to, I've seen it used in butler applications, kind of used at like parties and stuff like that to balance liquids. And the one thing that this could really be used for is it could be used in hazardous situations, and it benefits from an exceptional turning radius. So the specifications that were developed at the beginning of this process, they were all included in the end user's needs. I needed 100% reliability, meaning that the system would maintain stability 100% of the time. I needed a power supply lasting greater than 20 minutes. I wanted to weigh less than 5 pounds, cost less than $500, less than 2 feet tall. And the transient responses that I had chosen, I wanted to have less than a 1.5 second settling time, as well as I wanted it to maintain stability after initially starting from a 15-degree offset. So the requirements that were developed, the operating condition, I wanted to run in a normal indoor room condition. The problem is once you start implementing the IMU, the gyroscope, once you change levels of temperature and humidity, some of the offsets will change from that. So it was important that I developed the system in room temperature, and it needed to continue to operate in that same environment. Other situations would change the outcome. For my legal requirement, I could not infringe on any existing patents. Safety, the consumer cannot be exposed to any risk of electrocution. The batteries that I'm using are capable of outputting up to 20 amps of current, so you can see that is a potentially dangerous situation for an end user. And to eliminate that, I needed to remove any potential short circuit possibilities. The energy sources, the battery must supply enough current to prevent possible brownout conditions. If the battery is not able to supply enough current, the motors will fail, as well as the microcontroller. And the engineering standard that I chose to highlight here was the I2C communication standard. It's a very, very common standard between microcontrollers and the peripherals, and it is capable of transmitting data at up to 400 kilobits per second. So now I'll move on to my component limitations in the process of ordering and choosing my parts. The microcontroller was chosen first. I chose to use an Arduino. It's a very, very common microcontroller. There's a vast wealth of information available on the internet. So that was kind of a no-brainer to stick with that. And then from that, all my other choices trickled down. The one thing that I really needed to take into account was cost. Once you're starting to get into DC motors and IMUs, things can become very, very expensive if you're looking for very, very accurate components. So the motors, as you will see in my simulations, they needed to supply up to at least 0.2 Newton meters of torque to meet the settling time specification. And the power supplies, for the microcontroller, the input to the Arduino Uno, it ranges between 7 to 12 volts. And for the motors, I needed approximately 12 volts. And each motor, the inrush current, or their starting current, is 2.14 amps. So I needed 4.28 amps to be able to supply both motors together. And the IMU, I needed at least 2 degrees of freedom. And this, I'm using the Z and X axis. So I needed 2 on the accelerometer and 2 on the gyroscope. So we'll move forward to my level 2, my final functional decomposition. And in here you can see all of the components that I had chosen. I chose the SEN10121 IMU, which is a combination of the ADXL345 and the ITG3200. And you can see here, it's basically a flow diagram, and you can see that we go through the algorithmic filtering, as well as my PID controller. And the output to here is the actuator voltage, which will be going up to my motors. In this functional decomposition, you will see on the left-hand side that I have a PID controller attached to the motors, which is for the encoder. That was never actually able to be implemented, but that this is what the final functional decomposition consists of. So before I started my simulations, I needed to gather enough information as to what exactly I was trying to solve for here. So you can see here, this is the image that I had initially shown you of the design that I had made. And you can see that the lateral position is denoted by x dot, and x double dot, which is the position, velocity, and acceleration. And the offset from the z-axis is going to be my angular velocity and angular acceleration. So here, before I explain this, I'm going to give credit to a student named Richard Oy. He graduated from the University of Western Australia. He was a graduate student, and he had come up with this model for part of his thesis. But basically what this is the model representation, the mathematical model representation of the inverted pendulum. You can see here, it looks to be very complex. This is only the incorporation of the wheels, motor, and pendulum components. And you will see here at the bottom, I did label exactly what it represents. Most of these, some of these were constants that were just gathered from data sheets or some slight mathematical derivation. But on the next slide, I will show you the most complex part that I had to derive was the inertia of the pendulum. So basically what we have here on the top is the equation for a hollowed rectangular prism. And you can see here, I was able to measure all of these parameters using a micrometer for the pendulum. However, on the top equation, you can see the variable for density. And this piece of metal was just laying around my house. My dad supplied me with it, and I didn't have, without experimentation, I did not have what the actual density was. So I was able to find the next equation for mass. And you can see that equation can be easily manipulated to substitute the density into the top equation. And from that, I was able to gather the inertia of the pendulum. Now, the last equation I have here is the parallel axis theorem. Now, in the first calculations that I had done for that inertia, that places your inertia at the center of the pendulum. However, I want the inertia with respect to the center of the wheels. So what I had done was, using this equation, I was able to transfer the center of the inertia down to the base of the wheels, and that could be incorporated into the state space representation. On this next slide, this is the process that was taken to get the transfer function in the frequency domain from the state space representation. You can see here that equation there is used to do that. So after using the matrices that were located in the prior slide and plugging that in there and putting that into MATLAB, I was able to derive my two transfer functions, one for the position and one for the angle. And these are the transfer functions in the frequency domain which represent my system. So I pushed forward with my simulations. This was done in MATLAB and SisoTool. You can see here that with the transfer functions that were located on the prior slide, this is the transient response that you would get from an impulse input. You can see that these are unbounded graphs, which is a clear indication of instability, which is what we expect, right? If there's no control placed on this system, it will fall to the ground. So on the next slide, I went ahead and I found the pole locations. This is what we expect. We have a pole in the right half plane, which is an indication of stability. So I moved forward and I obtained the root locus from that transfer function. And you can see here that we are indeed in the right half plane, which is my reason for instability. And what I did here is I created parameters. You can see the shaded yellow area. That is where I do not want my root locus to be in to meet my specifications. And the vertical line that you see here, this is to meet the 1.5 second settling time. And I believe that the triangular portion there is, I put a percentage overshoot requirement of approximately 15%. So I used a pole placement controller using the state space representation, and the controller that I had originally designed, the poles were placed at -5 plus or minus j, as well as -6 plus or minus 2j. And you can see here in this graph that my root locus now stretches into that portion of the plane that I would like them to be. And from this, on the following slide, you will see the transient response after this controller was designed. You can see here that I do have approximately a 1.5 second settling time. The behavior of the system is stable, so this is what I was looking for. So as an engineer, I wanted to push forward and see what more I could get out of this design here. I'll get to that in another slide or two, but here what I had done is I determined what the control input was for that particular controller to obtain that transient response. And you can see here that the magnitude of this is 0.2052 Newton meters. And through looking at the data sheets of my motors, I can have up to 0.329 Newton meters of torque. So what I did was I moved those poles further into the left half plane at -8.5 plus or minus j, as well as -9.5 plus or minus 2j. And you can see here that I was able to get very close to that maximum torque that the data sheet told me that I was able to achieve. So on the following slide, if I were to design the controller based on that, I would be able to achieve a 1.1 second settling time, which far exceeds my initial specification. So now I'll move on to the testing that was required. First, I had tested the motors and encoder. The encoders needed to be implemented in order for me to gather data from my motors, so they were done concurrently. The initial attempt was a failure. I thought that at one point I thought I had a hardware failure and a software problem. And what was happening was I didn't attach interrupts in the beginning, so the microcontroller was getting confused between the A and B channel. So for instance, if I was reading 1-1 at one point, and then a period of time went by to run the loop, and if it read 1-1 again, the microcontroller got confused, and I wasn't able to gather a correct encoder count. So I did a bunch of research, and I was actually able to find a library called Digital Write Fast. Using this, it uses direct port addressing, and I was able to increase the read and write time by 13.73 times. As it turns out, like I had said, at the end it was determined that it was just an interrupt problem. So the interrupt was implemented, and then I was able to successfully test my motors and encoders. So this shows you what I did to test them. I ran a loop through the Arduino IDE, and what I did was I took samples from approximately 2 seconds and 7 seconds, and I took all of that data and averaged it together, and I ran a little bit of dimensional analysis here, and for one of the motors I was able to get 434.9 RPMs, and I did that for the other motor as well. So then I moved to the data sheet of the motors to see what I should be getting, and you can see here that the data sheet told me that the best case scenario I would get 8,240 RPMs under no load conditions. My motors have a 14:1 gear ratio, and they're rated at approximately 70% efficiency. So using those numbers, I was able to get that I should be getting about 412 RPMs. So on the following slide, you'll see I created a table here for the percent error. These are slightly larger than I was initially anticipating. 6.19 and 7.45%. However, I kind of chalked this up to the loose terminology of efficiency. The data sheet had said that they were approximately 70%. This is showing me that they're actually slightly of higher efficiency than that. But as it turns out, when all this was said and done, and I went through all that trouble of the interrupts, I ran into a problem. And the problem was that the motor shield that I had chosen, it's the Arduino Motor Shield R3, it inconveniently uses a pin of that for the pulse width modulation of the motors that the Arduino uses as one of its 2 interrupts. So that effectively deleted one of the interrupts that I would be able to use. So then I moved on to the IMU testing. This was very, very, very difficult for me. It was entirely software based. I don't have a very good software background, so this took me an extended period of time. I did all the coding, and it wasn't as responsive as I knew that it should be. And it turns out after several weeks and many, many hours of trying this, it turned out that it was one very, very small bug in my program. And after that was fixed, worked beautifully, and I was able to move forward. And on the next slide here, you will see the visualization that I had used to see what kind of data that I was actually getting from this. It put out a nice 3D rectangle on the bottom. And you can see here on the top, we have 5 different numbers that were output. On the bottom left, on the left, RW accelerometer and RW gyro, as well as RW estimate. Those are normalized vectors that were given from the algorithm. RW acceleration is obviously from the accelerometer, and gyro is from the gyroscope. And the RW estimate, that is the estimation that was given from the filtering algorithm after all the data was processed. And then on the top right, you'll see that these are the real-world values. The gyroscope was given in degrees per second, and the accelerometer was given in degrees. So I'll tell you about what I had done for the actual IMU testing. I will precede this with saying that this was a pretty poor test on my part. I probably should have done something different, which I'll get to in a moment. But what I had done here is I determined which angle the pendulum was actually at that point in time, and then I gathered the reading from the computer of what the IMU was telling me where it was at. And I did that from -45 up to +45 degrees. But you can see here that between -5 and +5, that those are pretty high percent errors. And this is due to the offset that was originally given when I started my testing at 0 degrees. You can see that right off the bat it had a 0.52 degree offset, and that error had carried throughout. However, I did confirm this. If all of those values that I do have there, they are all very, very, very close to 0.52 degrees offset from where I expected it to be. So I'll move on to the filter testing. The first test I had done, throughout all of my research, I knew that the common filter was definitely the most reliable filter that I could use. So the first test that I had done was on the common filter. But you can see here the problem is that the microcontroller with its 16 megahertz clock speed was not able to keep up with all of the linear algebra that was required of the common filter. So you can see here there's a time delay between peaks, and what's happening as a result of that is the IMU output is never able to give a true reading of where the position of the pendulum is at that variable. So then, from that I had decided that I was either going to use a complementary filter or a hybrid filter, which I actually wound up using. But after all my preliminary testing was done on my subsystems, I proceeded to move forward on my system testing. This shows you the output with the motors off. I held my project up, the motors were off, it was not touching the ground, and I just moved it I just oscillated it back and forth. And you can see here that the output from the filter is very smooth. There is a slight time delay there that did come out in after several iterations of testing, but you can see that there's a little bit of noise that's given off. The blue line there is of the accelerometer. That was one of my main concerns throughout this entire process. And you'll see in the next slide that what I had done is I turned the motors on, and the first half of the graph here is with the motors on, but me still moving it in the same fashion. And you can see here that there is fairly large spikes in the accelerometer, much vibration, much noise. However, when I had placed it on the ground, the right half of this graph shows you what happened. It moved in a very violent fashion. It just shook back and forth. And what was happening is that the backlash and the vibration that was carried out throughout the system to the IMU was just giving me garbage results. So as a result of that, I needed to come up with a solution. And what my dad had helped me with is I made two structure alterations. The first was done on the base of the robot. Pieces of insulation were placed between the motors and the base of the robot. And then the following slide shows the changes that were made to the IMU. Initially it was placed on the wheelbase. I wanted to move it up a little bit to hopefully not accept too much of that vibration. There was a piece of rubber placed underneath the breadboard which housed the IMU, as well as a piece of rubber placed between the bracket and the pendulum as well, and it was secured tightly to the pendulum. And you'll see here in the next slide that this is the result of that. You'll see the resolution of this graph is much, much lower than it was before. You can see it's choppy behavior. It was done with the normalized vector as opposed to the degrees, but at any rate, you can see that much of that vibration was dampened as a result of these structure alterations, which is what I was looking for. So, the final data that I was able to achieve, this graph here, this was done in Excel. What I had done is I gathered the angle rate, the angle values from 0 degrees up to 0 seconds up to 2200 milliseconds. And what I had done is I started it off at approximately 45 degrees and I brought it up. My control loop tells the pendulum to kick on once I hit 15 degrees, which you will see here at the beginning part of my graph. At 15 degrees, the system starts to attempt stabilization. This was done at a 50 millisecond control loop time, which shows you that's the reason why this is such a choppy graph. At every 50 milliseconds, it's telling my data, where the pendulum is currently located at. So you can see here that it's attempting stabilization. The problem that I ran into at the end is that because of all this vibration and the backlash from the motors, I had to place a heavier reliance on my gyroscope. And gyroscopes, the problem with them, whereas the accelerometer has problems with noise and vibration, the gyroscope suffers from drift. So you can see here in the right portion of my graph, if you were to average all that data out, you would see that I'm at a slightly negative angle, which is as a result of the gyroscope. So now I'll go through my cost analysis. At the end, all these components added up, I came to $512.77, which I will show you at the end failed my specification rather of not exceeding $500 by $12.77. And then this shows you the amount of time that was spent from the spring until now, all the research and the design and everything that totaled up to 452 hours. At $60 an hour, that would have been $27,120, giving me a grand total of $27,632.77. What was estimated in EE 405 was that I would spend approximately 380 hours, and my components would have cost me $390. So the difference between those two is I wound up going over the projected cost by $4,442.77. Here we have a Gantt chart. It shows you the amount of time that was spent on each part of the process. You can see the first one that I have up top there, that was all the simulation, design, and modeling that was done. That took the longest period of time. Several times I had to go back and forth depending on changes that were made to my system. But what I really want to talk about here is the last two portions. Although they look fairly small, that is where a large bulk of my time was spent within these last few months. That was all the testing that was done on my subsystems and the final systems and the coding and trying to retune it. So that comprised of a large portion of the total time spent. So now I'll go through the actual what passed and what failed out of my initial specifications. First I'll go through the failures, and I will make a slight change here, but because I was not able to achieve 100% reliability, as a result of that, any sort of transient response specification would also fail as a result of that. Because unless you have an entirely stable system, you can't really assign a settling time requirement or anything like that. So, so obviously I failed that all drift must be eliminated. I showed you in the previous slide that was a failure. I went over my cost. It's not operational 100% of the time. It's not reliable. It's not 100% stable. And then also, that I consider that one of my transient response specifications, that it would be able to stabilize after an offset of 15 degrees. And also on the top, in my report, I had left that as inconclusive. It probably should be considered as a failure, what I had said before as far as my settling time requirement. So conclusions and future work. I am disappointed that the project was not fully completed the way that I had anticipated it being. I spent a very, very, very large amount of time on this. So to end up at the end with something that is not what I had envisioned is disappointing. I feel that I should have taken less length of time, definitely, for the simulations. The thing is with this project, right? We know that segues exist. We know that IMUs work. So I knew that this was going to work, right? Unless I chose very, very poor motors or something like that. I knew that it would work. However, part of engineering is doing the simulation before that to make sure that it will work, right? A client asks you to build something for them, you want to be sure that it does work. So the biggest thing that was overlooked was the backlash. After purchasing these motors and constructing everything, I did some research on these motors, and it turns out that they have an average of 1.2 degrees of backlash, which is slightly higher than other motors. So that's probably something where I should have spent a little bit more money or did a little bit more research to find motors that have less backlash, and that would have caused much less headache. Another solution to that is if I had my wheels driven by belts rather than directly off the motor rotor, that would have also eliminated some of the vibration as well. So moving forward, if I am able to solve that vibration, I would then be able to place a heavier reliance on my accelerometer, which would effectively eliminate the drift caused by the gyroscope. And then after I was able to achieve 100% stability for the angle of the system, then I would be able to move forward to implement the encoders. The code's already done for the encoders, just the PID controller currently has gains of 0, so it's not implemented. And then after that was done, then I would be able to successfully control the position as well. So before any questions, I'll just do a brief demo here. I'm hoping that I'll get some decent results. Sometimes it works fairly well, sometimes it doesn't, but what you're going to see here is if I'm able to get a somewhat decent stabilization of the angle, you will see that it's going to drift back and forth laterally which is what I had just explained, that the encoders are not implemented, so there is currently no control placed on the position at all. So you can see it's attempting to stabilize the position, but it's moving back and forth because the position is not currently being controlled. So what's happening is, and I've run this for lengths of time, and over time it just starts to drift. It'll go like 10 feet in one direction and then 10 feet in the other direction, and eventually it's not able to keep up with the velocity of the system, and it will fall down eventually. But right now, I mean, it's actually giving some decent stabilization for the position. But you can see that after some time, it does start to lean in one direction. And that is what was described in that graph that I had shown with the drift that is implemented due to the gyroscope. So that concludes my presentation. If anybody has any questions for me?
Any question? Does it operate differently on different surfaces?
Yes.
If you're on a smooth surface right now, I'm thinking maybe the tires are slipping or not giving enough traction.
Yes, I'm actually glad that you asked that. Before I had even done a large majority of my work, probably back in like September, I had initially run it on carpet, and it ran perfectly. It would move maybe about 6 inches one direction and then 6 inches in the other direction, but it would hold a upright position for minutes, you know. And but what happened was is as soon as I placed it on a hard surface, that's really when the backlash started to affect the results of the IMU. So what I gathered from that is that initially when it was on carpet, the carpet did a very good job of damping the vibration caused from the backlash of the motors.
Was there any calculations made on friction, slippage, anything like that?
It was not. The state space model that I had originally shown you, that went under the assumption that it was a frictionless system. So yeah, that was not incorporated at all.
And one other thing, sure. But the length of the upright, was that calculated into everything, or?
Yes.
Okay.
Yep. That was in.
Because I was thinking, well, maybe you had too much weight, that's why it wants to roll over.
Oh, yeah, I see what you're saying. Really, that wouldn't make too much of a difference. See, the thing is that the simulation that I had done, that was done all in state space. But it was done in the frequency domain as well. But this currently has a PID controller in it, and that PID controller was not designed in the simulation. But basically what I'm trying to say is independent of the length, as long as those motors can supply enough torque to overcome the inertia of the pendulum, it should be able to achieve stability.
I can add something to that. Sure. Based on his model, if you have seen this modeling, there are some parameter like L, right?
Yes.
Which represent the length of the bar that you have over there. The system by itself is unstable, so you cannot do much about it. It's unstable. But the location of the pole to the right of the j omega axis depends on the value of L that you have. The longer or the taller the bar is, the unstable the system is. So here it is. Fundamentally, the system is unstable. But it's better for you to stabilize the system which the pole is closer to the j omega axis if it's a shorter system, right?
Correct.
So that's it. And the other question that you have, you're absolutely right. When you put it on the carpet and you put it on a slippery surface, there are two different models basically. And again, this is not part of his project. It's some sort of mechanical engineering to go ahead and model that slippery effect of the wheel. It is there, it does have some impact, but he managed to design a system which works fine on both surfaces. Right?
Is there anything that you feel you have yet to learn to complete the project?
I feel that I should probably do a little bit more research on the algorithmic filtering. It is fairly complex. I know I had done a technical paper on that, so I do have a very, I'd say a fairly decent understanding. But really, like I had said to start off with, the Kalman filter would be my best bet. From my understanding through my research is that the Kalman filter is more of a dynamic filter. So it would basically change its estimation based on the amount of noise given from the accelerometer, which you could see that from the graphs that I had shown before that would really, really help me in this situation. So to answer your question, the thing that I would probably want to learn more would be the Kalman filter, which shown through my testing, I would need a faster microcontroller to implement that, but that would be the one piece that I would really want to learn further.
Anybody else? Okay, well, thank you.